Let's go through LeetCode 1696 jump game 4. And it gives us the integer randoms. And initially, you standing at index 0. And in one move, you can jump at most k steps forward. And once you are at index, you are able to collect the score. So it asks what return the maximal score you can get. So, for example, example one, we and k that is we the step, right? So initially we stay at 1, and then we can choose in the next either -1, -2. We choose -1, right? And -1, and then at least at most k step we choose 4 and 3. Then the total score, the maximum score is 7. So for this question, we should be easily thinking about using dynamic programming, right? So for the we need int dp array dp, right? For example, this equals new int n, and the dpi will represent the maximal score which we get at current index, right? So dp, the transition function will be from the j is from I minus k to I minus 1, right? Um, the maximal dp, right? And max of this dpj and the plus nums I, right? So in the end, what we return is just dp n minus 1, right? Uh, so doing like this, so here there is one for loop that is I iterate from 0 to n minus 1, right? But for every j, it has k iterate k items, right? So in that case, it will be O n k time complexity. And for this kind of range, you'll see the n and k is 10 to the power 5 range. So it will be TRE, right? So we should have some more efficient way, right? So we'll see actually this kind of DP array, those kind of DPJ, right? It is also a sliding window. It is a fixed size sliding window with size k, right? And for this kind of, so we have a DPI. What we want is the previous k DPs, the maximum value, right? So we can, for example, use a tree map or tree set heap or those kind of ways to find the maximal of DP for this kind of range. But as we know, we just want to find the max, right? Not many high values, top values. We can use um, monotonic deck, right? So for this question, we'll see we are looking for the previous, not include I, previous K, the highest DPJ, right? So we know for those kind of order is that we are firstly, before we'll put in queue on the right as a last step. So the first step is we check the left boundary to see if this kind of index, the deck pick top, whether it is out of boundary, right? Whether it is still in the range of k. If it is out of boundary, then we pull from the left. And the second step is if this deck, because doing like this, it's possible it is empty. So we need to check if the deck is not empty, right? Then our DPI will find one of the in the previous K, the Harris one, right? The empty case is let me see. If we iterate I from 0, right? There is nothing on the previous data structure, then that will be empty. But if you don't actually from from the index from after one, right? It will never be empty. So in that case, of course, you can also write some corner cases for DP0, right? But if we don't want this kind of special case, we just check if this is not empty, then pick. So the highest top J, it is on the peak of the left values. And after that, we process the DPI, right? DPI will be add our highest previous one. And the third step is we add this DPI to our data structure. And we pour out of this, those kind of DP which is smaller equal current DPI from the right, right? So because for those kind of in the data structure, if the index is smaller or equal to it is smaller than DPI, and the DP value is smaller equal to DPI, the index is smaller than I, right? It will never be used for the future calculations. Will never be used as maximum values for the future, right? Because even equals, we can still use DPI as a maximum value. So let's write code for this. We let's have int n equals nums dot length, and we need a deck integer p equals new array deck. So we need let's have a dp right, new int a. We are looking for the maximum value. Of course, we can initial this one as all of the value to be some kind of negative or not negative because it's integer mean, right? But the thing is that because this kind of DP, we'll see will be calculate from every value we are going to calculate from previous one. So it is fine that we don't initialize as all of them as minimal value. So what we do is that for int I equals to 0, I smaller than n, I plus plus, right? So we'll say if this stack is not empty. So here it is empty because in the future when we let me see. Just for the first one, right? First zero index, it is possible in the empty. So if it is not empty, and if this kind of index minus deck.pick first is greater than k, right? Then we can get rid of those kind of data from the left side, right? So we are able to have deck the poor first, and then we have the things that we have DPI. We are add equal to current norms, right? And then what we do is that if this kind of deck is not empty, we are going to have DPI, which is plus equal to the previous largest. So will be DP deck pick first. Now what we do is that we add this index to that deck from the right side, right? So for the deck, we are looking for the DP fixed size window maximum. So now what we do is that the thing is that because when we check here, this will be a bit different. The order will be different in the fixed sliding window median because for that one, what we want is current index I is included to find all of the max. But for this one, what we need I is not included, right? So the order is that we'll first check boundary, then do processing. And because I is not included, after that, we'll add this kind of I to our uh, deck. So what we write is why this deck is not empty, and deck dot so DP, right? So DP deck peak last. If this is smaller equal to current DPI, right? Then we are safely to pull them out from last. And we also, after that, we should add the last index from the right. In the end, what we need is just a return dp n minus one, right? And let's also write a Python code for this. So we know we need a deck data structure. So let's just first write from collections import DQE, right? So what we need is, for example, let's have n deck, n equals length of nums, deck equals a deck. Let's call it a DQ. So DP equals this one multiplied by n, right? So what we do is that for in range n, then we'll say if DQ is not empty, and this is just for the first index, I minus DQ 0 if this one is greater than k, right? We have so the thing is that why we need to check whether this one is great to k, because in the future when we add, it is possible on the poor right we'll have the this kind for this kind this the top of the deck one will being poured from the right, so the size is less than k, right? So we need to check deck top left, and then we'll write dpi equals nums I. So let's say if dict is not empty, we have dp I. We should add equal to deck dp deck 0. So this is deck, this is dp, right? And now what we do is that we need to pull from the right the kind of useless element. So y deck and dp deck minus one is smaller or equal to dpi. We can safely remove this kind of things from the right, and we don't need we do not forget to append the index I to it. And in the end, what we need is return dp n minus one. It will be on time complexity and on space on space complexity, right? And for this deck, that is k, right? So but we for this dp it is on actually. Actually, this one, we don't need to have size n, we can have size k, because when we calculated the previous k items, right, the the order, some of the, because that is just a slide in Windows. So actually, if we have the size k dp, should be fine as well, right? Because the previous one will never use in the future calculations. So we can get a space complexity improve a little bit, right? But they are in the same range. So you have size n. They are same range to our 10 to the power 5s. So you're right. This is fine. So um, time complexity is O n, and space is also O n.